Hi folks, this is Linear Algebra, Checkpoint Quiz 14. We're given a function from the polynomials of degree 2 or less, including 0, to R2, given by this formula. T of at squared plus bt plus c, that polynomial goes to this column matrix, A over B minus C. Now, it turns out this is a linear transformation. You can go ahead and verify that. And so part A, we're asked to find a basis for the kernel of t. So we have to remember, what is the kernel of t? The kernel of t, by definition, is going to be all vectors in the domain, so that's P2, that get sent to the 0 vector in the codomain. Okay, so what does that mean? Well, to be a vector in P2, that means that you're an AT squared plus BT plus C, so that T of V, which is A over B minus C, is the 0 vector in R2, which is 0, 0. Okay, so really that's what we're looking for, is the polynomials where this is true. So this is going to be all AT squared plus BT plus C, where, well, A clearly has to be 0, and then B minus C has to be 0, or in other words, B equals C. And so if I write that out, A is 0, so he's gone, and B and C are the same, so I can just call this BT plus B, which is B times t plus 1. And so really what I've done is I've written this as a span of just one polynomial, one vector, t plus 1. So that means I can take a basis for the kernel of t to just be the polynomial t plus 1. So that'll do it for part A. Alright, so part B now, we're asked to expand the basis we found in part A to a basis for P2. And so we basically have to expand the set t plus 1 into a basis for P2. Now remember, we have a theorem that says given any linearly independent set of vectors in a vector space, we can always beef it up to a basis for the entire space. Since P2 is a three-dimensional space, I need to add 2 vectors to this to get it to a basis for P2. Alright, so I'm going to start building it up here. I think it's fairly obvious one vector that's not going to be in here that we're going to need is t squared. So I'm going to add t squared to that. I think it's pretty clear that t squared is not in the span of that. Now I have to bump it up one more time. I got to add one other linearly independent vector in there. That's not going to be in the span of this. So if I think of what the span of this is going to be, is it's going to be alpha t plus 1 plus beta t squared. And so I'm going to have polynomials that look like beta t squared plus alpha t plus alpha. So as long as I can pick a polynomial that doesn't have this pattern to it, I'll be fine. And so if I just throw in the constant 1, 1 is not in the span of this. So that means that these are going to be all linearly independent. And since I have 3 of them, and the dimension of P2 is 3, I know that this is a basis for P2. So that'll do it for part B. Okay, part C, we're asked to use our answer to part B to find a basis for the image of T. This goes back to the proof of the dimension theorem we had in class last week. Basically, we've got a basis for the domain, which is built up of a basis for the kernel, and then a basis of things that aren't in the kernel. And so we know from that proof that a basis for the image of T is going to be T of the vectors that aren't in the kernel. So that's T of t squared and T of 1. So now I just go through and compute these. T of t squared, using this formula, A is 1, B and T are 0. That's going to give me 1, 0. T of 1, A is 0 and B is 0. C is 1. That gives me 0, negative 1. So a basis for the image of T is all of this. And just as a little side note, this means that the image of T has got to be all of R2, because it's going to be the span of these, and these are two linearly independent vectors in a two-dimensional space. And actually we knew that from the dimension theorem, because the dimension of the domain is 3, the kernel is dimension 1, that means the image is dimension 2. And since the range is two-dimensional to begin with, that means the codomain's two-dimensional to begin with, that means the image has to be the whole thing. Okay, so that'll do it for quiz 14.